Okay, so in section 1.10, we're going to talk about measures of position. We're also going to talk about the empirical rule. To bring us up to speed a little bit, what we've discussed so far is we've discussed how to describe a data set, right? We talked about how to measure the center and the dispersion of a data set, as well as how to describe its shape. We've also discussed how to compare two data sets. So the third sort of main topic for this chapter was to be able to describe individuals within data sets. So there are really kind of two questions that we want to answer in this section. First of all, we want to know how an individual compares to other individuals within the same data set. And then the other thing we'd like to be able to do is compare individuals from different data sets and see how they stack up relative to the individuals within the data sets they come from. So we'll talk about each of those things. One way to describe the position of an individual within a data set is to use what we call quantiles. And we've actually already seen a certain type of quantile already. We've seen quartiles in the past, but the main tool that we use when we're trying to compare individuals is not the quartile, but rather the percentile, which is something you've heard of before. But anyway, there are different kinds of quantiles, right? We could have tertiles that split a data set into 3 parts, or quartiles, as we've seen, which split a data set into 4 parts. Quintiles split a data set into 5 equal parts, and so forth. Percentiles are going to split a data set into 100 equal parts. Okay, and about 1% of the data is going to be in each of those chunks, right, that are created by the 99 percentiles. In general, about k% of the data is below the kth percentile. Okay. Now, you may recall that the first quartile has 25% of the data below it, and so Q1 would be the same thing as P25. Okay. In a similar way, Q2 has 50% of the data below it. That makes it the same as the median, and both of those things are equal to the 50th percentile. And then finally, Q3 would be equal to the 75th percentile. So let's practice just interpreting percentiles in the next couple examples, and then I'll show you how we can compute percentiles in Excel. So this first example here says, Jennifer just received the results of her SAT exam. She scored at the 74th percentile with a 600 on the math portion. What does this mean? Give an explanation in words and in math symbols. Well, to score at the 74th percentile means that she scored better than 74% of people who took the test. So we could say something like Jennifer's score of 600 was better than 74% of test scores that year. In math symbols, we could say something like P sub 74 equals 600, right? A score of 600 is at the 74th percentile. Okay, here's another example. You take your 6-month baby boy to the pediatrician for a routine checkup. The pediatrician tells you that your son is at the 57th percentile for height and the 4th percentile for weight. What does this mean? Do you have reason to be worried? Well, so if the boy's at the 57th percentile for height, that means that he's taller than 57% of boys his age, right? Of 6-month-old baby boys. So your son is taller than 57% of babies his age. Note that that also means that he's shorter than 43% of babies his age. Okay, but that's pretty average, right? That's almost right smack dab in the middle of the pack. For weight, on the other hand, he's only at the 4th percentile. So your son is taller than 57% of babies his age, but he weighs more than only 4% of babies his age. Or in other words, right, he weighs less than 96% of babies his age. And that might be a reason for concern, right? It means that he's on the smaller side for weight, and so maybe he has some kind of nutritional issues that need to be resolved. So his weight may be cause for concern. Okay, but his height is totally normal. So that's how percentiles work. You'll encounter percentiles in the real world in situations just like this, with test scores, with doctor's appointments, and things like that. Let's see if we can figure out how to compute some percentiles in Excel. We're not going to do this by hand. We'll just use Excel to do this. And so the function that we're going to use in Excel is the percentile.inc, right? Percentile.inc function. And we'll have to select the data, okay? And then we'll also have to enter in the percentile that we want Excel to compute for us. The percentile will be expressed as a decimal. So for example, if you want the 20th percentile, then k will be 0.20. And for the 7th percentile, k would be 0.07. Okay? Now, sometimes we want to go the other way around. Sometimes we want to get the percentile rank k. And so instead of giving Excel a value and asking what's its percentile, sometimes we'll be given the, other way around, right? So for a percentile, we'll be given percentile rank k, and then we'll be asked what percentile goes with that. We might want to go the other way around, though. We might want to start with the value and say what's the percent rank of that value within a data set. So I'll show you examples of both things, and it'll become more clear what I'm talking about as we look at some examples. So this one says, use Excel to complete the following tasks for this data set. So here's our data set. We're not even told what these numbers represent. Okay, we're just given some generic data, and we're asked to find the 6th and 90th percentiles. In other words, P sub 6 and P sub 90. So for P6, we're going to use the equals percentile .inc. Okay, and then we'll open up a set of parentheses. We'll choose our data, and then we will put in the percentile rank. We want the 6th percentile, so I'm going to enter that as 0.06. Okay, and we'll see what Excel gives us. P90 would be the same, right? Or not exactly the same, I suppose, but similar. Okay, so let's head over to Excel and see what we get. So here's our data set, and I'm just going to click into an empty cell, and then I'm going to say equals percentile.inc. Okay, so I'll scroll down and choose that one. I'll hit tab, and then I will select my data. Okay, so I'm just going to click and drag, and then I'm going to hit comma, and I'm going to put the percentile rank that I want, which is the 6th percentile. Okay, so there you go. This is the value that would be at the 6th percentile. Okay, a 42.56. For the 90th percentile, we would do something similar. We would say equals percentile.inc, choose our data, and then comma, and I want the 90th percentile, so I'm going to put 0.90. And there you go. A value of 84.4 would be at the 90th percentile. So let's write those down. Okay, so 42.56 and 84.4. Okay, were our answers. So there's the 6th percentile and there's the 90th percentile. Okay, part B asks, the observation of 82 is at what percentile? And what about the observation of 42? Okay, so this is one where we're asked to work backwards, right? Because we're given the observation and we're asked for the percent rank, right? The percentile. So this time we'll say for 82, okay, we'll use the equals percent rank .inc, okay, and again we'll select the data and I'll put in 82 for the value. Okay, for 42 I would do something similar. %rank.inc, choose the data, and then enter in 42. Let's see what we get. Okay, so for my value of 82, I would say equals %rank.inc, that's that function down there. I'll hit tab, select the data, and then comma, and then I want the percent rank for a value of 82. So a value of 82 would be at the 88th percentile, roughly. Okay. For a value of 42, I would do the same thing. I would say equals %rank.inc, choose the values, comma, and put in 42. Okay, so for a value of 42, the percentile would be about the 4th percentile, approximately. So I have the 88th percentile and the 4th percentile, approximately. Let's write those down. So this is about the 88th percentile. In fact, it was 0.884, I think. So this is the 88th percentile. Ooh, and the other one was 0.038. So this is about the 4th percentile. Okay, and I guess I don't need an approximation sign because Excel gave me exactly 0.884. Okay, so that's how we would figure out percentiles and percentile ranks. Doing so gives us a way to compare the rank of individuals within different groups. Okay, so for example, Eduardo and Jimena both run track. Eduardo ran the 400 meter in 50.37 seconds, and Jimena ran it in 55.72 seconds. The other finishing times are as follows, right? So this is the finishing times for the men, this is the finishing times for the women. We're asked to compute the percent rank for Eduardo and Jimena, and then answer the question, who did better relative to their sex? So clearly Eduardo ran faster than Jimena, right? He finished about 5 seconds faster than Jimena did. But the question is Eduardo's time among men better than Jimena's time among women? Okay, that's the question that we want to answer. So we'll compute the percentile ranks for both of these individuals, and then whoever has the lower percentile rank did better, right? They finished faster. So let's see. So for Eduardo, I'm going to use the equals percent rank .inc function. Okay, I'm going to put in the data set for the men, and then I'm going to put in his finishing time, right? Because I want to know what the percent rank is for his finishing time. So that's 50.37. We'll see what we get for Eduardo, and for Jimena I'm going to do a similar thing. For Jimena, I'm going to select the women, and then I'm going to put in her finishing time, right, 55.72 seconds. Let's see what the percent ranks are for these two individuals. Okay, so for Eduardo, I'm going to say equals percent rank .inc. I'm going to choose the men, and I'm going to put in Eduardo's finishing time, 50.37. Okay, for Jimena, I'm going to say the same thing, equals percent rank .inc. I'm going to select the women's finishing time, and then put in Jimena's finishing time, which is 55.72 seconds. Okay, so it looks like Eduardo is at the 39th percentile for men, and Jimena is at the 26th percentile for women. So Jimena is closer to the top of the pack than Eduardo is, right? Jimena is closer to the top for women than Eduardo is for men, which means that relative to their sex, Jimena did better. Okay, so let's write those down. We'll say Eduardo's at the 39th percentile, Jimena is at the 26th percentile. So Jimena was at the 26th percentile, approximately, and Eduardo was at the 39th percentile, approximately. Did I get that right? Yes. Okay. So this means that Jimena did better relatively, right? Okay, she ran the race faster. Okay, so that's how we use percentiles and percent ranks to compare individuals in different data sets. Another tool that we can use to do the same thing is the z-score. And the z-score is especially handy if you don't have raw data to go off of, because in order to get the percentiles and percentile ranks, you need some raw data, but sometimes you just have like a theoretical distribution to work with, and that's where the z-score really comes in handy. So the z-score of a data value is the number of standard deviations that value is above or below the mean. If you have population information to work with, then this is the formula that you would use, right? The z-score is the number of standard deviations from the mean. So you first find the distance from the mean. This is the observation minus the mean, right? That gives you the distance from the mean. And then you would divide that by the standard deviation to give you the number of standard deviations that distance is. This formula is saying exactly the same thing, but it's using sample statistics instead of population parameters. So it's still observation minus mean divided by standard deviation. Obviously, if the data value is larger than the mean, then the z-score will be positive, right? If x is bigger than mu, then x minus mu will be a positive number. If the data value is smaller than the mean, then the z-score will be negative for the same reason. And the reason that I point that out to you is just because the z-score is signed. So if it's a negative number, then that tells you that the observation is below the mean, right? And if the z-score is a positive number, that tells you that the z-score is above the mean, or that the observation is above the mean. Okay, let's just practice a little bit with this concept. As we all know, the mean length of unicorn tails is 52.1 centimeters, and the standard deviation of the length of unicorn tails is 3.5 centimeters. If a unicorn appears in front of you and says the z-score for the length of her tail is 2.3, what does this mean? So this is a pretty likely scenario, right? Unicorns appear to you all the time, and when they do, they're always talking about z-scores, aren't they? Well, okay. So a unicorn appears in front of you and says that the z-score for her tail is 2.3. Okay, so that means that her tail is 2.3 standard deviations above average, right? It's 2.3 standard deviations above the mean, above the typical, length. Now, that's maybe a little bit confusing. I think this is confusing to students at first because they say, oh, so you're saying the standard deviation is 2.3. But no, that's not what I'm saying. We were told that the standard deviation was 3.5. What I'm saying is that her tail is 2.3 standard deviations above the mean. So if the mean is 52.1 and one standard deviation is 3.5, then 2.3 standard deviations would be 2.3 times 3.5. That's how far above average she is. And in fact, part B asks us to calculate that number. It says, how long is the tail of the unicorn from part A? Well, her tail would be the mean plus 2.3 standard deviations more than that, right? 2.3 standard deviations above the mean. So we're going to take the mean and add 2.3 standard deviations. In this case, again, the mean was 52.1, and the standard deviation was 3.5. So we're going to do 52.1 plus 2.3 times 3.5. Let's head over to the Desmos calculator to figure out how much that is. Okay, so we're going to do 52.1 plus 2.3 times 3.5. And there we go, 60.15. And this is centimeters. Okay, so 60.15 centimeters. Part C asks, how many standard deviations below the mean is a unicorn with a tail that is 480 centimeters long? How many standard deviations below the mean is a unicorn with a tail that is 480 centimeters long? Well, this doesn't make any sense at all because the mean was 52.1 centimeters, right? So 480 centimeters is not below the mean. That's way above the mean. I think I probably meant to say 48.0. In fact, I'm going to go ahead and make that correction. So in your notes, it'll probably say 48.0. Anyway, how many standard deviations below the mean is a unicorn with a tail that is 48.0 centimeters long? Well, that's exactly what the z-score measures, right? The z-score measures how many standard deviations above or below the mean a particular observation is. So we'll just use the z-score formula, right? We'll say, well, the z-score is going to be x minus mean divided by standard deviation. in this case, our observation is 48. The mean is 52.1. And the standard deviation is 3.5. So again, I'm going to have to go over to Desmos to figure out how much this is. So let's do that. And I'm just going to type it in exactly the way it looked on my page. To do that, you could go ahead and click on this little fraction thing to give you a fraction bar. And then you can type in 48.0 minus 52.1. And then arrow down to the denominator and put in 3.5. And that's it. A common mistake that students will sometimes make here is they'll say something like 48 minus 52.1 divided by 3.5, and you notice that when you do that, Desmos is only going to divide that second number, and that's not what you want. You want to divide the whole thing by 3.5. So you have to do it the first way that we did it. You could do this with parentheses, I guess. You could open up parentheses and say 48 minus 52.1, close the parentheses, and then divide by 3.5, right? That'll do the trick as well. But just make sure that at the end of the day, what you type into Desmos matches what was on your paper, okay? So our answer should be negative 1.17. We usually round z-scores to 2 decimal places, so we'll call it negative 1.17. So how many standard deviations below the mean is a unicorn with a tail that is 48 centimeters long? Well, it's 1.17 standard deviations below the mean. Okay? And that's how the z-score works. Here's how we can use the z-score to compare two individuals from two different data sets, right? This one says, which is a relatively better score? A score of 75 on a history test or a score of 27 on a psychology test? Scores on the history test have a mean of 80 and a standard deviation of 12. Scores on the psychology test have a mean of 30 and a standard deviation of 8. Well, I'm going to go ahead and compute the z-score for both of those test scores, and whichever z-score is larger is relatively better. Okay, so we had a history test and we had a psychology test. For the history test, the score was a 75. Oh, let me just write out the formula. X minus mu over sigma. Okay, so the score was 75, that's X. The scores on the history test have a mean of 80, so the mean is 80. And they have a standard deviation of 12, so I'll plug in 12 for that. I'll punch that into Desmos here in a second. For the psychology test, let's do the same. Our z-score is X minus mu over sigma, right? Observation minus mean divided by standard deviation. For the psychology test, the score was a 27, which seems a lot lower than 75 until you realize that the psychology test average was only 30, right? So it has a lower average to begin with. And then we're going to divide by the standard deviation of 8. Okay. So let's go punch this into our Desmos calculator. So for the history test score, I'll have 75 minus 80 divided by 12. And for our psychology test score, I'll have 27 minus 30 divided by 8. And you'll notice that neither one of those test scores is very good. They're both below average, right? Because they're both negative numbers. So neither is a good score. But I think that this test score is closer to 0 than this one is, so it's a little bit better, right? They're both below average, but this one is further below average than this one is. So this one is a slightly better test score. That was for the psychology test, I think. But let's write these down. So again, rounding to 2 decimal places, we would say negative 0.42, and negative 0.38. So this is about negative 0.42, and this is about negative 0.38. And since the psychology test score is closer to average than the history test score, right? It'll be it's a slightly better test score. There's not much of a difference, but we'll say the psychology score is slightly better. Okay. So that's how z-scores work. So we've talked about percentiles and we've talked about z-scores, and they can both be used to describe the position of an individual within a data set, and they can also be used to compare how two individuals from different data sets stack up to each other relative to the data set that they come from, right? So they're both useful. The last thing that I want to talk about in this section is the empirical rule, which in some sense kind of ties these two concepts together in a way. What the empirical rule says, well, it tells us how much of our data we can expect to fall within certain z-scores, right? So it tells us what percentage of our data falls within certain z-scores. So it kind of marries percentiles and z-scores together. Here's what it says. So for bell-shaped data, approximately 68% of all data values are going to fall within one standard deviation of the mean. Okay, that's within one z-score. All right. Approximately 95% of all data values fall within two standard deviations, so they're within two z-scores. 95% is almost all of the data, right? So if an individual is more than two standard deviations from the mean, that individual is pretty unusual. Okay. And then finally, 99.7% of all data values are going to fall within three standard deviations of the mean. So they're going to be within three z-scores of the mean. Now this fact only applies to bell-shaped data. If the data are not bell-shaped, then you shouldn't use this general rule of thumb. Here's a picture that shows the empirical rule visually. Okay. So we've got 68% of our data within one standard deviation. So if our mean is in the center, then one standard deviation above the mean would be at mu plus sigma, right? Mean plus standard deviation. And one standard deviation below the mean would be mean minus standard deviation, right? So this is one z-score, right? We've got 68% of the data within one z-score of the mean, within one standard deviation. Now, because the bell-shaped distribution is symmetric, half of that 68% is going to be within this region, right? So half of 68 is 34, and the other half is in this region. And that's how we get those numbers. 95% of the data are going to be within two standard deviations of the mean. 68% of it is already accounted for here in the middle. So the remaining, what would this be? 27%, okay, are in these two regions, but that's a 27% that's equally split between those regions. So 27 divided by 2 is 13.5. That's how we get those numbers. Anyway, you don't need to memorize these numbers, by the way. I'm just pointing out how we get them. But 95% of the data are within two standard deviations. That would be between mu minus 2 sigma, right? This is two standard deviations below the mean, and this is two standard deviations above the mean, right? So 95% of the data fall inside of this range. And then similarly with three standard deviations, right? 99.7% of the data is within three standard deviations. And that's how the empirical rule works. Let's practice applying the empirical rule a little bit. So number 7 here says, Subway cookies have a mean of 24 chocolate chips and standard deviation of 3 chocolate chips. If a cookie is 2 standard deviations below the mean, how many chocolate chips does it have? Okay, 2 standard deviations below the mean. Well, you could figure this out just using a formula, right? You could say if they're 2 standard deviations below the mean, then we would start with the mean and we would subtract off 2 standard deviations. Okay? In this case, that would be 24 minus 2 times 3, which you could plug into Desmos, but this one is easy enough. I think I can do it in my head. I know that 2 times 3 is 6, and I know that 24 minus 6 is 18. So if a cookie has 18 chocolate chips in it, then it's 2 standard deviations below the mean. Okay. Part B says, about 68% of cookies will have what range of chocolate chips in them? Oh, okay, 68%. Well, that's what the empirical rule, that's one of the things the empirical rule tells us, is that 68% of values are going to be within 1 standard deviation. So, about 68% of cookies will have what range of chocolate chips? Well, anywhere from 1 standard deviation below the mean to 1 standard deviation above the mean. Okay? Again, you could do this with formulas. You could say 1 standard deviation below the mean is the mean minus a standard deviation. That's 24 minus 3 in this case, which is 21. And 1 standard deviation above the mean would be mu plus sigma, right? The mean plus a standard deviation, that would be 24 plus 3, which is 27. And so we can say 68% of cookies will have somewhere between 21 and 27 chocolate chips in them. Okay. So 21 and 27. Well, finally, part C asks about what percentage of cookies have between 21 and 30 chocolate chips. Well, we know that 68% of cookies will have between 21 and 27 chocolate chips. 21 and 30 is a little more challenging, but if we go back to that diagram on the previous page, I think it will help us. So, we know that the average cookie, the average Subway chocolate chip cookie, has 24 chocolate chips in it. So I know that for the Subway, was this Subway? Yeah, this was Subway. So for our Subway example, we know that the mean is 24. So I'm just going to label that with a 24. We also know that a standard deviation is 3. So if I'm 1 standard deviation above the mean, I would be 24 plus 3, right, chocolate chips, 27 chocolate chips. If I'm 1 standard deviation below, that would be 24 minus 3, right, 21. If I'm 2 standard deviations above, well, 2 times 3 is 6, right, and 24 plus 6 is 30. If I'm 2 standard deviations below, it would be 24 minus 6, so 18. And then finally, if 1 standard deviation is 3 chocolate chips, then 3 standard deviations is 9 chocolate chips. So if I'm 3 standard deviations above the mean, then I would be at 24 plus 9, which is 33. And if I'm 3 standard deviations below, it would be at 24 minus 9, which would be 15. You'll notice that the distance between these numbers is 3, right? To get from 24 to 27, we add 3, 27 to 30, we add 3, 30 to 33, we add 3. That's because each of these is 1 standard deviation apart, right? And a standard deviation in this case is 3 chocolate chips. Anyway, to answer the question though, we were asked about what percentage of cookies have between 21 and 30 chocolate chips. Well, 21 is right here, and 30 is right there. Okay, so the percentage of cookies with this range of chocolate chips in them is going to be 34 plus 34 plus 13.5%. Okay? Well, 34 plus 34 plus 13.5. Let's see how much that is. (34 plus 34 plus 13.5) is 81.5%. So we would say about 81.5% of cookies are going to have somewhere between 21 and 30 chocolate chips in them. Okay, so we have covered percentiles, we've covered z-scores, and then we've covered the empirical rule, which kind of ties those two concepts together. Tells us what percentage of data we can expect to fall within a certain number of standard deviations. So that'll do it for this section. I will check back in with you again soon.